Welcome everybody. Today our lecture, which is lecture 6, will be about memory access optimization. We previously started this course about how we can optimize memory accesses in a system on chip. So today we will continue this topic. Previously on system on chip design course, we focus on memory. So memory is an important component in a system. Okay, so there are a lot of different components like a processor, peripherals, and memory is the most important one. So basically we need to optimize our memory system in order to increase the performance. So memory sometimes can be bottleneck for application, especially for memory intensive application, because they access the memory intensively. So you need to understand the well-known techniques to improve your system. So we just looked at this before, and we also looked at how we can scale the memory before. So we just started how we can improve the latency, and there are some techniques like scheduling and data reuse. So in scheduling, we just overlapped memory operations and compute operations. So if you are not optimizing or if you are not creating a scheduling for your application, so they are like sequentially executed. So but while an compute operation can be overlapped with the memory operation, you can increase the performance. We looked at before. So we also looked at how we can exploit the data reuse available in our applications. So basically, suppose that you have a lot of different arrays in your applications, and some of the memory references for these arrays can be reused. So you don't need to go for each memory references to a global low speed memory. So you can just bring them into your closed small memory, which is very fast. So you can exploit and you can reduce the overall latency of your small memories. So we looked at scratch pads and actually we looked at a motivational example in order to understand how a scratch pad optimizes our application. So this is like a local memory. You can just attach a local memory into your system and put some of the arrays in this local memory. Then you can decrease the amount of memory references you have when you compare with the original one. Okay, today we will continue to study on memory. Okay, because there are also other techniques which are more general, like latency engineering with data caches. Okay, or sometimes in processor there are also instruction caches, but caching is an important technique that exploits data reuse available in your application. Okay, so these are more general way of exploiting the data reuse in your system, in your application. So we also look we will also look at bandwidth engineering, how we can engineer the bandwidth, because we have bandwidth, a fixed bandwidth to access to our main memory or disk. So is it possible for us to optimize it? So we will look at wide word and banking in order to increase the performance, and especially for in terms of bandwidth. So in memory access optimization, memory bandwidth, which we are also called throughput, and latency sometimes can be bottlenecks. So you need to improve them. Okay, so in order to improve it, so you need to minimize your data movement. Okay, so your application, if it has less amount of data movement, it is better. Okay, so in order to minimize this data movement, you can exploit the small and local memories which are very close to your CPU or your processing system. Then you don't need to go every time to a main memory which is slower than your local memories. Okay, so how we can exploit? So because of the data reuse available in our most of application. So if you can understand how we can exploit the data reuse, you can improve your application um, faster than before. So before we look at how we can optimize memory access it with caches, so we can just understand the performance of different types of memories. So there are different technologies for memory, like static RAM, which we call SRAM. These are available in our chip. So you can the latency between 0.5 nanoseconds and 2.5 nanoseconds, which is very fast, but they are very expensive. These are like $2,000 and $5,000 per gigabyte. But you cannot, you need, especially for today, you need 2 terabyte of information. So you cannot build such a memory just consisting of static RAMs. So it's not possible in terms of their in terms of your system budget. So but you can exploit, you can create a memory hierarchy having different types of memories. Okay, so there are also other types of memory like dynamic RAMs and magnetic disk. Dynamic RAMs, especially today in our computers, we are using as a main memory DRAM. Okay, these are like DDR types memories. Dynamic RAM memories, their latency is between 15 nanoseconds and 70 nanoseconds. So basically they are cheaper than the SRAM, like $20 or $75 per gigabyte. So as you can see, this is better, but it has like 100 times slower than the static RAM. But this is very cheap when you compare static RAM. So, but again, you cannot build a lot of like terabyte of your memory just consisting of static RAM and dynamic RAM. It's also very expensive. So there is also another type of memory like magnetic disk. We are using this storing huge data, but they are very slow. Like their latency in between 5 milliseconds and 20 milliseconds. Okay, so basically, but this is very low, but it is very good in terms of budget limitation for your system, because this is like $0.2 or $2 in range per gigabyte. Okay, but what is an ideal memory? Ideal memory is you would like to access time. You would like to have an access time like of SRAM, but you would like to have a capacity and cost of gigabyte of in terms of disk. Okay, so this is ideal, but you cannot build such a system because today's available memory technologies. But you can create a memory hierarchy consisting of static RAM, dynamic RAM, and magnetic disk, and understanding your memory accesses, and you can approximate, or you can reach the ideal memories if it is if your application has a lot of data reuse and good regular patterns. We will continue with DRAM technology because it's important. Why? Because we are using DRAM memories as a main memory in most of the system today we are designing, okay, or we are using. So data is stored as a charge in a capacitor in DRAM technology. So there is a single transistor which is used to access the charge. So not like SRAM. In SRAM we have like 6 different MOS transistor, but in this DRAM technology we have single transistor which is used to access the charge. This charge is actually the information that we are trying to access, but they must periodically be refreshed. During normal operation, the first command should be sent to the DRAM is typically an activate command. Okay, so activate command is essentially the row access command, which means that it opens up a row in your bank. Bank is just your DRAM memories are organized as banks. Okay, there are a lot of banks in your memory system. So the activate command selects a bank and row address. So accessing a row in a bank is always done before opening a column in DRAM. Okay, opening a row is higher priority. Another important thing on the activate command is that row is currently open remains until a precharge command is issued. Okay, so basically when a precharge command is issued, it means it deactivates the row which is currently open in your bank. If precharge is taken, then it means you need to open that row again if you want to access. Okay, so for every act command there is a corresponding precharge command has to be issued. Okay, the act command opens a row and pre command closes the row. This is important. So in active state, DRAM device can perform reads and writes because we would like to access a memory reference and we would like to read or write. Okay, but in terms of logical perspective, we don't know what kind of commands available in your DRAM, so we are just trying to read or write. But in the DRAM, inside of DRAM, there are a lot of different commands that needs to be issued, but these are all done by your memory controller. But you need to understand how DRAM memory is working, because these are limiting your performance, so you need to understand and understand how it operates and makes your system more DRAM friendly. Okay, so basically you can access sequentially. For example, in your application, if you can access sequentially, so it's better for your DRAM memory. You can exploit more performance from a DRAM memory. So DRAM is actually random access memory, but what is the difference between when you compare different random access memories is actually the capacitor used for memory storage will leak charge over time. So because of that, DRAM is dynamic because it needs to be periodically refreshed. This is where the refresh command comes in. Okay, DRAM refresh command is issued every so often. Okay, basically you don't need, because your memory controller is just issue these kind of commands, but please consider that there are a lot of different commands issued periodically, and this actually decreases your memory bandwidth.